Hey guys, welcome to chapter 18. We got a little bit of a review from chemistry here with sort of a physics twist. We're going to be dealing with units and how we're going to think about gas from a physics perspective. So we're going back to thinking about pressure. So if you are a little rusty on pressure, look back at our fluids chapters from the last section. And also, the math here is pretty easy. It's just algebra and a little bit of graphing. So if you need any review on that, that's a good place to start. We're going to be in chapter 18 of the textbook. This is the thermal properties of matter, and just getting started. Okay.
All right. So let's talk about the thermal properties of matter. All right. So microscopic versus macroscopic. Macroscale is objects large enough to see and touch. So when we talk about like pressure and force and volume, those are macroscopic quantities, okay? Microscale are objects that are too small to see with the naked eye. So when you're talking, so in terms of snow, right? Macroscopic is it looks like white paint all over the roof or whatever. And then microscopic is like an individual snowflake, okay? In terms of like gases, macroscopic is like, okay, the volume of air in this room. Microscopic is individual air molecules. Okay? So talk about equations of state and the ideal gas. So that some of this should be a little bit reviewy if you've taken chemistry. State variables, that's just a fancy way of saying the variables that describe macroscopic systems. Now remember, a system, how do we define a system? What's a system in physics? Whatever you say, that's right.
It's 100% true.
So you just set a boundary, right? So for instance, if you're talking about a gas, like let's say in a piston, the boundary could be the piston, the system is anything inside the piston, and then the environment is anything outside the piston, okay? So you just have to figure out your boundaries. That's a system, all right? So state variables describe macroscopic systems. So for instance, when we talked about the Coke bottle, the Coke inside the bottle was our system, okay? So that means we could figure out the volume of the Coke inside the bottle, figure out the mass, figure out the pressure, the density, the temperature, all of those things, okay? You can also figure out things like the heat, okay? So the definition of an ideal gas, it's a gas. It's a gas whose molecules don't really interact, except occasionally they run into each other, okay? But they don't, what we mean by they don't interact is some molecules are charged, right? So they could be attractive or repulsive. Ideal gas molecules aren't, right? They're basically just like, you can approximate them to be tiny spheres that just bounce around and fly around, okay? And if you're looking at the periodic table, where are your best ideal gases? Yeah, all the way to the right, that would be the noble gases, okay? Because those are all inert, right? They have full outer shells, so they're nice spherical looking atoms, and they just bounce around. And so those are all going to be monatomic gases. Then if you move over, you can get like the diatomic gases. What do we mean by diatomic? Two atoms, right? Two atoms stuck together, like any oxygen, right? Nitrogen. Those are all diatomic gases. So monatomic gases would be like helium, neon, argon, krypton, and not so much xenon. I mean, we don't really deal with xenon. Some of the higher ones, and then the diatomic gases are over just slightly to the left of those, okay? So, and then there's also like more atoms stuck together, and those get a little bit more complicated. We'll talk about all that stuff a little bit. Anyway, for an ideal gas, density is low, meaning there aren't a lot of molecules, so it's definitely a gas, and it's not near the condensation point, okay? Because if you're near the condensation point, you're about to become a liquid. That's not going to be as simple, okay? You're about to experience a phase change. So, state variables of interest, pressure. Now remember, P has lots of meanings here. P and rho are not the same. So P is pressure, rho is density. And then we have temperature, volume, and what's N? Moles, yeah. Okay. Question. You guys are good. The other class had trouble with this for some reason. Good. So it would shrink. Yay! All right. And why does it shrink?
They're going to be like expensive or Or they're closer together.
Why are they? Yeah, they move less, right? So if you're a hot molecule, what do you do? Yeah, look over, it's acting it out. You're like whoa, all over the place. Okay, as you get cold, you kind of like start moving closer in, not jiggling as much. And so the reason that when things move faster, they start to bounce off each other and then they expand. Okay, if you're not moving as much, you're not bouncing as much. You can contract a little bit. All right, so that's a microscopic thing that creates a macroscopic effect. All right, here's another question now. All right. You're killing it. Your lab partner is going to explode stuff everywhere. All right, and why? What are you increasing?
Pressure.
Pressure has nowhere to go.
What are you increasing first? Temperature, right? Which increases pressure. The previous time, you're decreasing temperature. What did you change? Volume, right? Volume. Also pressure. But, so what we're seeing here is a relationship between temperature, pressure, and volume, okay? If you change temperature, you change pressure and or volume, all right? Because this is pressure, this is volume, number of moles is usually constant. For instance, in the balloon, the gas isn't getting out of the balloon, it's just staying in there. If you close a flask, the gas isn't getting out of the flask, it's just staying in there. This is a constant, this is temperature. We use slightly different units in physics than we do in chemistry. Just a word to the wise. Pressure is in pascals, okay? Pascals are newtons over meters cubed, which is force over area, meters, volume. Force over volume? No. Newton over meter squared, force over area, okay? This is volume, volume's in meters cubed, okay? N is in moles, R is this, it's joules per mole Kelvin, okay? And then temperature is going to be in Kelvin. And make sure that you do that, because remember, when we're dealing with change in temperature, you didn't necessarily have to convert back and forth between Celsius and Kelvin, but this is not a change in temperature, this is a temperature at a specific point, so you will need to convert to Kelvin. Yes? This is the Maxwell-Boltzmann constant. Yes. So this is the same equation with a different constant. So this is still in pascals, which is newtons per meter squared. This is still in meters cubed. This is now N, which is molecules, okay, instead of moles. So this is like the number of moles. This is the number of individual molecules, okay? This is the Boltzmann constant. This is still temperature in Kelvin. So these are the only real things that change. The difference is in physics, like a lot of the time you're dealing with such small sample sizes that the individual number of molecules matters, okay? This is for like a more bulk situation. This is for like a very tiny amount of stuff, all right? All right. Okay, so we're going to do a quick example on the ideal gas law. Remember that is P, PV equals nRT. And here we're going to be focusing on units and what units we use in physics and how the units cancel. So even though this is a really simple plug and play problem, I'm trying to demonstrate the use of units. Now obviously in our steps we usually draw a diagram. You're not going to need a diagram for this. This is just simple algebra and units, okay? To start off with, when we're talking about standard temperature and pressure, that means temperature equals 0 degrees and pressure equals 1 atmosphere. But remember, in physics, we want to deal with Kelvin. So 0 degrees is the same as 273 Kelvin. And then the pressure is going to be 101 times 10 to the third pascals, because we don't want our pressure in ATM, we want it in pascals. We already know that N should be in moles, so that's 1.00 moles. Okay, and just for reference, this constant R is 8.31 joules per mole Kelvin, which is going to be important for canceling things out. So these are the things we know, and then we're looking for volume, and we want our volume to be in meters cubed, because that's the units we use here. Okay, so when we set this up, we know that we have our PV equals nRT,
and we're solving for volume. So that's going to be nRT over P. So fairly straightforward, we just plug things in. This is 1.00 moles. R is 8.31 joules over mole Kelvin, and temperature is 273 Kelvin. And we're going to divide this by our 101 times 10 to the third pascals. Okay, so some of the units canceling are pretty straightforward. You can see moles, oops, sorry, that slid. Moles cancels here, all right. You can see that Kelvin is going to cancel here. So we end up with something that looks like this. So 0.0224, but then we still have joules over pascals. So joules over pascals, that's just our units that we have left, if you want to look at that. So here we have joules and pascals. So we're just going to come up here and take a look at that. All right. So remember, joules is kilograms meter squared over second squared, and pascals is newtons over meter squared. It's force over area because it's pressure. Okay. Force is kilograms meters per second squared, and then area is meters squared. Now remember, this is the same as newtons, right? And we don't have to go into that, but if you want to look it up, that's what newtons breaks down into. You can get that from force equals mass times acceleration, okay, our Newton's second law. And if we want to break down how this works, now we have kilograms canceling, right? Then we have second squared canceling, and now we have a meter here and meter squared here. So this, oops, let me just use a different color. This cancels with this square, and now we have meter squared on the top and 1 over meters. So this whole thing should give us meters cubed, which is good. That's what we wanted here. Okay, so our answer is 0.224 meters cubed. Now, I'm just showing you this also as an example. It's a good way to look at units, but I want to point out that this value right here comes up a lot. So we often have problems with 1 mole of ideal gas at standard temperature and pressure. The reason for that is we live on Earth and standard temperature and pressure are pretty standard. That's why we even talk about them. So that's something that we can sort of assume. And so whenever you see 1 mole of any ideal gas at standard temperature and pressure, you don't necessarily have to do this whole calculation again. You can just assume that you're going to get an answer that looks like this. This is a good number to remember on top of what standard temperature and pressure are. Okay. All right, so here's our first problem. I'd really like for you guys to try to do this on your own and then just pause the video and then I'll go through it with you afterwards. It's important to do this because you need to try out problems on your own to really know if you can do them. So make an attempt at this, and obviously it says in this room, and we're assuming dimensions. This was written for an in-person class, but use your imagination. So just in a room of these dimensions. And make sure you really make an attempt to do this before you just follow along with my solution, because the only way to really know if you're understanding what's going on is to be able to come up with a way to do problems on your own. If you need help, you can go and then try to do it again. So even if you follow along with the solution, make sure you go back and try to set the problem up yourself. You don't have to solve all the algebra, but you do need to know how the basic setup works, okay? So hopefully pause, and now I will start to do the solution. So if you have been listening to this, pause here. Okay, so we have this room. It's 5 by 3 by 2.5. It's at 20 degrees Celsius, which is a pretty comfortable temperature if you're familiar with Celsius. And then we know the molar mass of air. So we can start by drawing a picture, although that's a little bit unnecessary here. But, you know, just for good practice, let's draw a picture of the room. So here's, the room is basically a box, right? It's a 5 by 3 by 2.5 meter box. So you don't really need to do this, but I like to draw pictures for these things. So here's our good practice, okay? So we'll say, okay, this is the 2.5 meters. The height will be 3 meters. And then the width will be 5 meters. All right. Now what do we need from this? Well, this is going to give us our volume. So our volume is going to be 5 meters by 3 meters. And you should really write out the sig figs, but you get the idea, 2.5 meters. And so that gives us a volume of 37.5 meters cubed. All right. And then we know our pressure is atmospheric pressure. So that's P, that's 101 times 10 to the third pascals. Remember, volume in meters cubed, pressure in pascals. And now our temperature is 20 degrees Celsius. So we add 273 to convert that to Kelvin. Remember, we need our units to be Kelvin. That gives us 293 Kelvin. Okay, these are our knowns. Remember, we're once again using the ideal gas law, so that's PV equals nRT. And so the thing is moles. We want to know the moles, because what we're looking for here overall is mass. Once we have moles, we know that we have this kilogram to mole conversion that we've been given. So the molar mass, which I believe is big M, is going to be 0.02900 kilograms per mole. All right. So that gives us a place to start. So known things, unknown things, and we know our equation that we're supposed to be using is the ideal gas law. Okay. So because of this, we want to solve for N. N is going to be PV over RT. So we just plug in our numbers. So our pressure is 101 times 10 to the third pascals. Our volume is 37.5 meters cubed. R is our constant, so that's going to be 8.31 joules per mole Kelvin. And our temperature is 293 Kelvin, which it's very important that it's in Kelvin, because remember, if you leave it in Celsius, you will be wrong. There's nothing there to cancel it. So at this point in the problem, we just have to cancel our units. So we can see that Kelvin's an easy thing to cancel. The joules per mole, remember this pascals is kilograms, meters per second squared over meters squared. So there's a lot going on there. You have meters cubed here, but we know what we're going to end up with is moles. So you can do all this. We're not going to go through the details, but you can see that pascals, joules, and meters cubed are going to have to cancel, and you're going to be left with just moles. Okay. If you want to work that out yourself, I'll leave that as an exercise for you to do. You plug all this stuff in, and this should give you 1,560 moles. That's going to be 3 sig figs, because you can see 3 sig figs here, 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 and this actually gives us 4 sig figs. So 3 is the minimum number. So we want to keep 3, whatever number we get here, we keep 3 sig figs, okay? So this is an intermediate step, because remember, we're asking for the mass of air in the room. Now we know the number of moles of air in the room, but we need the mass. So in order to get the mass, we have to convert, but we know we have something in kilograms per mole. So we take our 1560 moles, and then we multiply it by 0.02900 kilograms over moles. All right, you do a little bit of canceling here, moles, moles, and then you end up with just kilograms. So this is 45 kilograms of air. See, it feels so light in the room, like you're not being weighed down by 45 kilograms of air. But that's what pressure is, right? If you didn't have this weight of air hovering over you, you would implode, essentially. That would be rough. So we're always in, if you remember from the previous class, a hydrostatic equilibrium within our environment. Because remember, if there's no pressure outside, you explode. If there's too much pressure, you implode. So we want there to be atmospheric pressure because the inside of our body also is at atmospheric pressure, and we don't want to die. So that is our answer, 45 kilograms. You can check that that makes sense. Air is not super dense, but that would be a big room. Okay, so all of those molecules have to add up to something.
Let's try. Stoichiometry. You don't have to say stoichiometry in here. Okay. Just an okay. Well, you guys know it can be determined. Please discuss. We'll vote again. It's shifted. That's actually bad. Less people voted for the right answer. Okay, so let's think about what does it mean to have equal mass? Okay, because none of these. So we're looking at PV equals nRT. Okay, so PV equals nRT. What do we know is constant? R. Yes. R is constant. P and V are constant too. So we're only adjusting N and T. If N goes up, what happens to T? It has to go down, right? Because this has to stay constant, okay? So these have to always multiply to the same thing, okay? So if N goes up, T goes down. If N goes down, T goes up, okay? So larger N means a smaller T. Now how do we determine N? We know these things have equal mass, okay? What do we know about helium versus nitrogen? Helium is lighter than basically everything except hydrogen, okay? So we know helium is lighter, which means if we have the same mass, which one has a bigger N? Helium. Why? Yeah, you need more pieces of helium to get the same mass, right? Because helium's lighter, so you need more of them, more particles, that's right, that's the word, particles of helium to get the same mass as less particles of nitrogen. So that means your N for helium, bigger, okay? What does that mean about the temperature for helium? Lower, okay? So if we have more helium, it has a lower temperature, which means the temperature of helium should be lower than the temperature of nitrogen. Yeah, well, you can also, you can look at it that way too. No, because there's always going to be, if it's the same mass, you're always going to have more helium particles than nitrogen particles. Do you see what I mean? So as long as your N is bigger, then your T is smaller. Okay. All right. Cool. Short. So let's talk. Basically, when we're dealing with an ideal gas, we're making a lot of assumptions. If you want to get a little bit more complicated, you have to use this thing called the van der Waals equation, okay? Which is if we change these things so that they're no longer these little point particles, all of these little molecules have interactions, right, as they bounce around, okay? The size of the molecules is determined by this term. The interaction of the molecules is determined by this term. And this also takes into account the fact that molecules have a physical size. Right over here, when we talk about an ideal gas, we ignore the physical size of the molecules. And so we have to subtract that off the volume and all this other stuff. I'm showing you this. You don't need to memorize it. I just want you to know that it's a little bit more complicated than PV equals nRT, and here are the corrections. Okay. A is just a constant. So B represents the volume of a mole of molecules, right? So you subtract the total volume of the molecules from the volume of the container. And A represents the attractive intermolecular forces. So remember, molecules are usually made of atoms which have positive and negative charge, so you end up with forces that interact with each other. So you have to get rid of the pressure, you have to subtract off the molecular interactions. To fix the volume, you have to subtract off the actual size of the molecules.
So is N still moles?
And still moles, right? This is still pressure, volume, nRT. So this is still PV equals nRT, but we're correcting pressure, and volume for like real world things. Okay, and just like we've said before in physics, physics is we start with the simpler model, right? We start with the simplest model, and if that doesn't work, we add back in the complexity. Okay, and here is some complexity. All right, we're not going to do anything with the van der Waals equation, but I would like you to see it because if you go on in engineering, it sometimes comes up. So now you've seen it. Okay.